Okay, then let us start today's session. Uh, First of all, let me introduce myself. I am Tanmay Sharma, a Prime Minister's Research Fellow from Mechanical Engineering Department of IIT Patna. And in today's session for the course NPTEL course IC Engine and Gas Turbines, we'll be learning about a few concepts about gas turbine and solving a few problems related to the gas turbine efficiencies and the work outputs and everything. So let us start today's session. Now let us talk about an open cycle gas turbine at first. What do we mean by an open cycle? So open cycle means that the the cycle is not following a continuous, there is no continuous cycle. So what do we mean by that is that the air which comes into the compressor gets into the combustion chamber, gets heated, and the heated gas now goes into the turbine, and after that it is released from the exhaust. But this same gas is not recirculated back into the compressor, so there is an open cycle. The cycle is not closed. So that's what we mean by an open cycle gas turbine. And in an open cycle gas turbine, the components which we will be learning about is the compressor, the combustion chamber, and the turbine. So basically, the air which also carries oxygen. So this air goes into the compressor. The compressor, the main job of the compressor is to compress the gas. It will raise the pressure of the gas from P1 to, let's say, P2. So in 2 dash, it will be in a state of higher elevated pressure, and this high pressure air will go into the combustion chamber, and it will add up with the fuel and get heated up, and accordingly a combustion will occur into the combustion chamber, which is generally at a constant pressure, and this combustion will lead to the generation of a gas and very high temperature and high pressure, and this very high temperature high pressure gas will then go inside the turbine and it will expand, and when it is expanding it will release its higher enthalpy state to and there will be enthalpy difference. Its enthalpy state will get decreased, and that enthalpy difference will be transferred into a mechanical work. So it will rotate the turbine, and accordingly some amount of this work will be consumed in rotating the compressor, and accordingly we will have a net work which goes to the output of the power plant. And the gas which has now expanded is still, although at higher temperature, but it will be released from the exhaust. But later on we will see that this exhaust gas can also be reused, so that the energy which is lost from the exhaust gas can be reused and the efficiency can be increased. So this is what an open cycle gas turbine is, and this is the TS diagram of the open cycle gas turbine. Here we can see that there are two pressure curves. This is the P1 pressure curve, that is the lower pressure, and this is the P2, which is the higher pressure curve. So what happens is that air in, this is the point 1 or state 1, the inlet condition, and after that when it moves to 2. So we have studied till now that the processes can be, if there are no losses, means there are no losses in the heat transfer part and in the work done. So what happens is that that process is called as isentropic process. So if we if we are able to nicely insulate this whole compressor, and we do not let the heat to escape while it is being compressed from P1 to P2, then the process is isentropic, and the isentropic process will have a constant straight line curve. This is 1 to 2 at constant entropy, isentropic process. But generally the processes are not isentropic. We cannot fully uh, prevent the heat loss, and hence there will be some loss while it is being elevated to pressure P2, and due to which the process is not isentropic, and it is rather an irreversible adiabatic process, and it follows a path from 1 to 2 dash like this. So here the state of the air is in 2 dash. So here at the elevated pressure P2 and at this particular entropy, And then when it goes into the combustion chamber, it gets heated up. Along with the fuel, there is a combustion, and this gas will now have an increased enthalpy, and the pressure and the temperature and this temperature of the gas will increase in a constant pressure process from 2 dash to 3, as you can see in here. So this is a constant pressure process, and or isobaric process, and you can also find this particular question in your uh, weekly assignments. So that's the answer to that. So this is an isobaric process where the heat is added up to the gas, overall gas, and the combustion takes place as constant pressure, and from 2 dash the whole air plus fuel, that mixture or the gas, will get its temperature elevated to the position 3, the property 3 and the state 3, and from point 3 it will go into the turbine. So the 3 point is the inlet to the turbine, and after that you can see that the gas expands, meaning the pressure now decreases from P2 to P1 out here. And if the turbine would have been completely heat loss proof, there is no heat loss, then it would have been an isentropic process in the turbine, and the process would have been represented by a straight line, vertical straight line in the TS diagram, which actually represents a constant entropy process or an isentropic process 3 to 4 from pressure P2 to P1. But that is not the case in ideal system. There are certain efficiencies, this yes, the certain efficiencies related to turbines and compressors, and due to these efficiencies, the process inside the turbine does not follow a isentropic path. Rather, it will be a irreversible adiabatic path, and the the gas now at state 3 will will expand to point 4 dash by this non-isentropic process, as you can see here, that is irreversible adiabatic process 3 to 4 dash. And after 4 dash, this whole gas will now be exposed to the ambient, this energy whichever it is at present. So you can see that the 4 dash, the state of 4 dash, has a higher temperature in comparison to the inlet state. So that means we are losing some amount of energy, and we are not able to utilize the entire energy as that compared to the inlet conditions. So we are losing some amount of energy into the surroundings, and that is and that we need to make sure that that energy loss is very less in order to take care of the efficiencies. And we will later on learn that in certain methods like regeneration, we can utilize this particular energy, and so that we can go very near to the inlet conditions, and that way we can save the energy which is coming out from the exhaust gas. So this was the TS diagram of the open cycle gas turbine, and these are the processes which I have already told you. Now let us check the performance of an open cycle gas turbine. So this part is quite necessary for the tutorials which I will be conducting in this session towards the later part. And for that, you just have to the most easiest part in a gas turbine is that you need to find the temperature. If you get the temperature, if you know which temperature difference represents what kind of work or heat process, then you can directly solve for the open cycle gas turbine. Like the work input in a compressor, so this is the work input, and the work input is basically within the temperature limits 1 and 2 dash, and we will simply have this enthalpy difference Cp T2 dash minus T1. This is the enthalpy difference in the compressor. So this is the work input to the compressor, and the heat supplied in the combustion chamber. So heat supplied to the combustion chamber is within the temperature limits 2 dash and 3, and this is also having an enthalpy change. Rather, the enthalpy is increased as the heat is added. So that is Cp into T3 minus T2 dash. Then then we can have a work output in the turbine, and that is being governed within the temperature limits of 3, state 3 and state 4 dash. So we will have the enthalpy difference between these 2 points, and that is represented by Cp into T3 minus T4 dash. So Cp means specific heat at constant pressure, and we also know that for enthalpy at a particular state, the enthalpy equation is given by Cp into temperature. So that is the formula of the enthalpy, and this is the enthalpy difference. And by this enthalpy difference, we are actually having either work or heat. Next, the thermal efficiency of the system is given by the net work output by the heat supplied, and by net work output we mean the work output by the turbine minus the work output by the compressor, because the turbine is also meeting the demands of the compressor, and accordingly the work that is coming out is not the entire work that is produced in the turbine. Rather, after compensating the work required by the compressor, we are getting a net work output. So this is the case: CpT3 minus T4 dash, that is the work in the turbine, minus CpT2 dash minus T1, and divided by the heat supply, that is CpT3 minus T2 dash. Thus the net work output is the work output minus work input, and the compressor isentropic efficiency eta com. So when we talk about the efficiency associated with a compressor or a turbine, so we will be talking mostly about the isentropic efficiencies. So that efficiency means is that how much it is deviating from an isentropic process. So for a compressor, 1 to 2 is an isentropic process, but it is deviating from the isentropic process as 1 to 2 dash, and how much it is deviating, that actually denotes the isentropic efficiency, and that is equal to the ratio of work input required in an isentropic compression divided by actual work required. So the work input required in an isentropic compression is between 1 and 2. So you will find that the work input required in an isentropic compression is between 1 and 2, so that is Cp T2 minus T1, and divided by Cp T2 dash minus T1. So that is equal to T2 minus T1 divided by T2 dash minus T1. So that formula we will use in many cases of the problem, rather in all cases, because in all cases we do not have an isentropic process, we rather have a irreversible adiabatic process, and in those processes we require a isentropic efficiency. So similarly, for an isentropic efficiency of a turbine, we have the actual work output, which is the 3 to 4 dash, and divided by the isentropic work output. So you will see that why the isentropic compression work input required by isentropic compression is in the denominator, while the isentropic work output here is in the here it is in the numerator, and the isentropic work here is the denominator. So you will have to understand that work input required by a compressor, we need it to be as low as possible, and the lowest we can get if the process is isentropic, right? See, so the 1 to 2 is a short, the temperature difference will be shorter, and a lesser amount of work is required. Rather, due to the inefficiency of the system in a compressor, the work is now getting increased. So to get the same pressure difference, we need to supply a higher amount of work. That's why we have to go traverse a part from 1 to 2 dash. That is, a high amount of work is required. That's why for a compressor, we have taken the efficiency as the actual which we required, that is 1 to 2, divided by the thing that we actually get, that is 1 to 2 dash. That is the actual work required. But in case of turbine, you see that the highest efficiency, highest work output from a turbine we can get through an isentropic process. You can see that 4 is a little bit lower temperature than the 4 dash. So although it is expanding between the same pressure limits, but it is not able to expand till the lowest temperature due to the heat energy that it is lost, right? So that's why the 3 to 4 is basically the isentropic work output, which is the maximum work that we can derive from the system, but rather we cannot derive it because of the irreversible effect of the adiabatic process, and we are left with the actual work output, which is quite less, that is 3 to 4 dash. So you see these are two are related, but obviously if you think, if you're getting confused, then you can think in this respect that an efficiency cannot be greater than 1. So you will have to think that a smaller term divided by higher term, and in compressor the smaller term is the isentropic part and the higher term is the actual work. In a turbine, the isentropic term is the greater term and the smaller term is the actual work that we get. So that's how the efficiencies are computed. So this is the formula for that. Now moving on to how to raise the efficiency of an open cycle gas turbine. And by efficiency, I do not mean only the thermal efficiency, but also to increase the specific work output. So sometimes specific work output needs to be higher rather than thinking about the efficiency. So there are certain methods like intercooling, reheating, and regeneration, and these three methods actually help in increasing the either the specific work output or the overall plant efficiency. And we will see how these methods work in actual practice. So let us first talk about intercooling. So in an intercooling, what happens is that uh, so the basic motto is that a compressor in a gas turbine utilizes the major percentage of work developed by the gas turbine, and the work required by the compressor can be reduced by compressing the air in two stages and incorporating an intercooler between the two. So the main motto is that since the net work is affected by the work which is compensated in driving the compressor, so that work, if we can reduce that work, then our net work output will be increased. In doing so, what we can do is that we can have two compressors rather than one compressor, and if we have two compressors, then the between the two compressors we will have a stage, that is the intercooler, which will cool down at a constant pressure the air which is coming out of the low pressure, and finally that air is an inlet to the higher pressure compressor, and it will further raise the pressure to the actual pressure that we want. And in doing so, the work required by the intercooler will be a little bit less, and we will see how. So basically this is the TS diagram of the intercooling stage. So what happens is that this is the inlet condition 1, and now what happens is that if there would have been no intercooling, then we would have directly gone from low pressure to higher pressure at by this process 1 to L dash. But since we are having two compression stages and an intercooling intermediate stage, so first there will be a compression from 1 to 2 dash, and from 2 dash point there will be intercooling, and from 2 dash the temperature will be reduced to 3 at a constant pressure, and after that there will be again a compression stage, so 3 to 4 dash. So then what happens is that there are two compression stages, and since the pressure lines are diverging to the positive entropy side, you see that this is having a higher slope, rather this is having a lower slope, and so the line at here is the line at here is higher than the line at here. So if you can imagine, then that this process raising the pressure from here to here at this process will be lower than raising a pressure from here to here, right? And that's why the work required in raising the pressure out here at this low temperature range is lesser in comparison the work required in raising the pressure in the higher temperature range, and that's how the work required by the entire compression process is reduced. And in addition, what happens is that yes, the work done is reduced, but now the amount of heat that needs to be added is from 4 dash to 5. So a huge amount of heat is required in comparison from L dash to 5, which was in a normal without intercooling stage. So extra amount of heat is required, like from 4 dash to L dash, and this amount of heat will actually affect the efficiency, not the work specific work output. But we will see how. So the work input with intercooling is Cp T2 dash minus T1. So T2 dash minus T1, this part, plus Cp T4 dash minus the T3. So T4 dash minus T3. So that is between intercooling. And without intercooling, we have Cp TL dash minus T1. So this TL dash minus T1, that can be divided into two parts, that is T2 dash and 1, which is same in both the cases, whereas this part is TL dash minus T2 dash, right? Now if we can compare the difference between T4 dash and T3 here is lesser than TL dash minus T2 dash here. So this part is less than this part. So the work input required in with intercooling is lesser in comparison to the work input required without intercooling. So the specific work output will be increased because the specific work output is the work of turbine minus the work in compression required in compression. Since the work required in compression is decreased in case of intercooling, so the specific work output will be increased. That part we have now know that okay, the work output will increase. What about the thermal efficiency? So if we compare now the thermal efficiency, now although the work output is increased, but high amount of heat needs to be supplied in order to raise the temperature from 4 dash point to 5, that is the inlet to the turbine. And while doing so, high amount of heat energy is required. And we know the thermal efficiency is work network divided by the heat supplied, right? Now the network in the numerator is increased, while the heat supplied at the denominator, that is now decreased, that is also has been increased. And that's why the thermal efficiency may remain constant or may decrease. Generally it is seen that while while performing the intercooling stage, the thermal efficiency generally decreases. So that's the case of improving the specific work output, but with compromising the thermal efficiency. Now we have the second condition, that is reheating. Now let us look at it. So reheating, in reheating, what happens is that, as the name suggests, the gas which comes out of the turbine will again get reheated and will go into another turbine. So there will be two sets of turbine, that is a high pressure turbine and a low pressure turbine. So the main concept is that the output of a gas turbine can be amply improved by expanding the gases in the two stages with reheater between the two. And the high pressure turbine drives the compressor, and the low pressure turbine provides the useful power output. Now, what happens is that high pressure there will be two stages of expansion, gas expansion, that is at the high pressure turbine and the low pressure turbine. And in the high pressure turbine, the work which is produced by the high pressure turbine will be entirely used to drive the compressor, while the exhaust which is coming out of from the high pressure turbine will be again reheated and then will be again added to the low pressure turbine, and the work output which is coming out of the low pressure turbine will be used to get the net work output. So that is the whole concept. And then we have a TS diagram of this process as like this. So there are two turbines, so but only one compressor stage. So 1 to 2 dash is the compression stage, 1 to 2 dash, and the pressure is increased from lower to higher pressure. Then at the combustion chamber 1, the heat energy raises the temperature from T2 dash to T3 out here, and this is the inlet to the high pressure turbine. As the gas expands in the high pressure turbine, it goes from point 3 to 4 dash, and in 4 dash stage So it will again go into the reheater, and there will be heat added in the at constant pressure from point 4 dash to 5, as you can see in here. Then at 5 it will again enter into the low pressure turbine, and at the low pressure turbine the gas will again expand from point 5 to 6 dash, and accordingly you will have the entire expansion stage from higher pressure to the lower pressure. So the thing here is that we know that while moving towards the right side of the entropy curve, the pressure lines diverges. So if suppose we have only one turbine unit, and the turbine here would have uh, expanded the gas from point 3 to directly to the lower pressure range, so the point 3 to L dash, then this would have been the temperature difference in the lower section. But with having a reheater stage, the temperature difference is 5 to 6 dash, which is greater than this temperature difference. So net work output that is derived from the two turbine stages is higher as compared to only a single turbine stage, and that will increase the specific work output. So you can see here the net work output with reheating will be CPG T3 minus T4 dash plus CPG T5 minus T6 minus CPA T2 dash minus T1. So CPA T2 dash minus T1 is that of the compressor. It will remain same in both the cases, but what will again from 3 to 4 dash. So here 3 to 4 dash will also remain the same in both the cases. The difference will be CPG T5 minus T6 dash in reheating, T5 minus T6 dash, then without reheating CPG T4 dash minus TL dash. So T4 dash minus TL dash. So that is without reheating. Now you can obviously see the difference since the pressure lines are diverging. The temperature difference here is higher than the temperature difference out here. That's why this value is higher in comparison to this value, as the net work output here with reheating will be higher in comparison to the net work output without reheating, right? So this is the case. Work output reheating is greater than work output no reheating. In that case, the specific work output is increased. But we have an increase in heat supply. We are using a second reheater, right? And by the use of the second reheater, we are actually increasing this amount of heat supply, CPG T5 minus T4 dash, T5 minus T4 dash. This amount of heat is needed in extra. So that way our thermal efficiency may decrease or may remain constant. So there may be a sacrifice in the thermal efficiency, but we are achieving specific work output as a whole. So this was the case how to again increase the specific work output by actually sacrificing some amount of thermal efficiency, or maybe or may not be considering an increase in the thermal efficiency. Then we come to the last case, which is the regeneration. Actually, pardon my mistake, this is the regeneration part. So this is regeneration now we are talking about, and the basic concept of regeneration is that the exhaust gases from a gas turbine carry a large quantity of heat with them since their temperature is far above the ambient temperature. Yes, the exhaust gas coming out of the turbine is having a very higher temperature as compared to the ambient temperature. Thus, so there is a huge amount of heat loss, so that they can be used to heat the air coming from the compressor, thereby reducing the mass of fuel supply in the combustion chamber. So basically what is being done is that the normal process would have been one, going inside the compressor, then achieving state 2 dash at a elevated pressure, then going into the combustion chamber. Now this is the combustion chamber, then going inside the turbine, and the exhaust gas coming out from the turbine is now having a very higher temperature compared to the inlet condition like in 1. Now what happens is that we will redirect this exhaust gas such that this higher temperature exhaust gas coming out from the turbine will be used to heat up the uh, compressed gas from the compressor before entering the combustion chamber. So if this will happen, the basic concept will be to transfer the heat to this region, and accordingly a higher amount of heat will be available before reaching the combustion chamber. Hence we will have to supply lesser amount of fuel or lesser amount of combustion energy in order to attain the same position like in 4. So PS diagram will be very helpful to make us understand this thing. Now you can see that, you can very well see that uh, and so from 1 it is compressed to 2 dash, and then 2 dash to 3 dash, 2 dash to 3, there is an heat exchange, and that's why in the heat exchange what happens is that there is a heat rise. The temperature raises, temperature of the compressed gas raises, compressed air, I mean to say compressed air, so it raises from 2 dash to 3, and this air now goes into the combustion chamber, mixes with the fuel, gets heated up, combusts, and the heat energy is released. And while the heat energy is released, the enthalpy increases from 3 to 4. So we are not now supplying the heat energy from 2 dash to 4, rather we are supplying from 3 to 4. So there is a reduced heat energy required. And then again at 4, this will be the expansion stage, and at 5 dash the exhaust gas will come out of the turbine. This exhaust gas will now cool to 6, and in the process of cooling it will impart the heat of this exhaust gas into the air in just coming out of the compressor. So that way the heat is regenerated, and that's why it is called as the regeneration. And in that way the net heat supplied is decreased. Since thermal efficiency is work by heat, if the denominator, the heat, is decreased, then for the same work output we are having higher thermal efficiency, and we will see to that. So since we are talking about regeneration, there is a term effectiveness associated with this regeneration process. So effectiveness means the increase in enthalpy per kg of air divided by available increase in enthalpy per kg of air. Now, increase in enthalpy. The increase in enthalpy is from 2 dash to 3, right? So that is T3 minus T2 dash, and we are assuming that the specific heats of CPA and specific heat of air and specific heat of gas are almost equal. So that will get cancelled out. So the net enthalpy will be simply the temperature difference now, the ratio of the net enthalpies. Now, T3 minus T2 dash, that is the increase in enthalpy of air, and uh, the net exchange of enthalpy should have been almost equal, or exactly equal, if there would have been if the system would have been 100% effective, right? So by effective we mean how much amount we need to supply to here. If means the exhaust is at 5 dash, so 5 dash to 6, we need to reduce the 6 to the ambient, and that's the amount of available energy that we have, right? But we are not able to supply that amount of heat directly to the compressed gas, because that the heat exchanger is not that much effective. In that case, the available increase in enthalpy would have been 5 dash to 2 dash, and we are not having that much means uh, effectiveness. In that case we are not able to increase the enthalpy that much. So that's why the effectiveness is T3 minus T2 dash divided by T5 dash minus T2 dash, and it is having a value lesser than 1. Now the such kind of system is now having a specific work output which remains almost the same, because we are not concerned with the work output. We are not uh, changing the conditions of the compressor and the turbine, so the work output remains the same. But for the same work output, the heat required is now less. That's why the thermal efficiency is increased. And a heat exchanger is usually used in large gas turbine units for man propulsion or industrial power. So this is an application of this regeneration method. Next, let us talk about closed gas turbine, closed cycle gas turbine. So in contrast to the open cycle gas turbine, a closed cycle gas turbine has its fluid working in a cycle. So you will see that the fluid inside the whole means the fluid that is concerned will first go to the compressor. It will get its heat from a heater. Then the heated fluid will go into the turbine. It will expand between the two pressures, and then the exhaust will come out, and the same fluid is now not suppose we have air in here, then it will not become gas after coming out of the heater, because that is having no contact with the outer ambience. So the fuel is not added into this loop. Rather, the heat energy produced from the fuel is indirectly supplied to the fluid inside the cycle. That's why the fluid remains the constant. Only the phase may change. Also, the phase will also not change, because uh, these are gas turbines and it is already in vapor phase. So the phase will also not change. Rather, the temperature, the enthalpy, the pressure, these will change, and of the same uh, this fluid. So a higher pressure fluid which enters into the turbine will be expanded to a lower pressure, and the lower pressure fluid, the same fluid, will be cooled down by a cooling medium, and again at the same time it will be cooled down up to the same inlet condition as one, and the cycle will continue. So this is a closed cycle gas turbine, because the exhaust is not released to the ambience. The exhaust is again entering into the compressor, and there is no pollution of the fluid. There is no mixing of the fluid with other outside uh, fuel or outside chemicals. So that is the this closed cycle gas turbine, and this closed cycle gas turbine actually operates in a constant pressure or Joule cycle, and this is the constant pressure or Joule cycle. This is the PV diagram, and this is the TS diagram. So in a PV diagram you will see that the pressure initially it is at pressure 1, and there will be compression, hence it will go to pressure 2, and then at the constant pressure it will get heat. Indirectly the heat will be supplied to that fluid. Then at pressure 3, the pressure will get decreased in the turbine 3 to 4, and after that there will be a cooling, due to which at constant pressure the temperature will be lowered from zero point 0.4 to zero point 0.1, which is the inlet condition to the compressor, and the cycle will continue. Generally the fluid is air, so air can be directly heated and cooled, that's no problem, and accordingly the cycle continues. And this is the TS diagram. Similarly, there's a constant pressure lines, and if this is isentropic, but rather these processes can be isentropic now, because a more controlled uh, environment may be possible. But even though these are irreversible adiabatic process, we can also solve for that. We know how to solve for that. We'll only have to utilize the efficiencies, thermal efficiency associated with the compressor and turbine. So that doesn't matter. So even if we consider this as an isentropic process 1 to 2, so for the better understanding of it, so this is the process. 1 to 2 is inside the compressor, 2 to 3 the heater releases the heat to the fluid, and 3 to 4 is the expansion process where the pressure decreases, and 4 to 1 is the constant pressure cooling process. So here it will again go back to the initial stage 1, and the cycles will continue. So the heat received is MP minus T2, and the heat rejected is MCP T4 minus T1. So the net work done. So the net work done is heat received per cycle minus heat rejected per cycle, and the heat received per cycle is this amount, heat rejected is this amount. So the thermal efficiency or the air standard efficiency can be calculated in this way, where the Cp is of that of Cpa, and that will be simply 1 minus T4 minus T1 divided by T3 minus T2. That is the air standard efficiency of a Joule cycle or constant pressure cycle. Then we can substitute T2 by T1, we can substitute these temperatures and we can bring it to a rather compressed form. We will see how. So T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. That is isentropic process. So we are considering air standard cycle, right? For air standard cycle, we generally consider that to be isentropic. That's why the isentropic process is shown. And for isentropic, that makes a job quite simpler, and we can use these thermodynamic relationships to condense this particular air standard efficiency in a very uh, small and simple terms. So from this we get the value of T2 to the in terms of the pressure ratio. Then similarly we can also get a relation between T3 and T4 in terms of the pressure ratio, as in here this is T3 T4. And if we put that together in this air standard efficiency above this formula, we will get a very simple form which is directly dependent upon the pressure ratio that we require. Simply the pressure ratio and the fluid that is used. So suppose the fluid is air, so we are considering 1.4 as the gamma, but if it is changed to another kind of fluid, then the gamma value will change. So the air standard efficiency is directly dependent upon the pressure ratio in which we need the operation to have, and the second is the fluid that we are using, the fluid property. So that's the thing about closed cycle gas turbine, how to calculate the air standard efficiency. And this is a note. We can also prove that the pressure ratio for maximum work to be possible is basically this. It can be related to the highest temperature T3 of the cycle and the lowest temperature T1 of the cycle by this formula. So this is related, and if we from engineering point of view, we can apply this to get the highest maximum work possible. Next, let us look at how a complete closed gas cycle gas turbine will look like. So that is a complete closed cycle gas turbine in which we will use the concept of intercooler. Then we will consider concept of this reheater, and then again we will consider the concept of regeneration that we have studied for open cycle gas turbine. And by that we can have a very good understanding of how to improve the specific work output as well as the thermal efficiency of the entire closed cycle gas turbine. So here you can see that this is the low pressure compressor. So that is the starting point. The air enters the low pressure compressor. There will be an intercooler stage. So basically here it is entering, it is getting compressed to an intermediate level. There is an intercooler stage in which the state 2 dash is cooled down to 3 at a constant pressure. Again then there is a high pressure compressor in which from 3 to 4 dash it is getting compressed. So you see from 3 to 4 dash it is getting compressed to the final temperature range, highest pressure range. And then from 4 dash, before entering into the primary combustion chamber here, so it is getting heat from the exhaust gas which is coming out of the lower turbine, lower pressure turbine out here. By that it is gaining some heat from 4 dash to 5 out here, 4 dash to 5. And in 5 the air and now the air is now getting combusted externally. So the fuel is not injected inside the loop. The fuel is externally this combusted, and the heat energy is uh, indirectly transferred to this air, and the air will get heated up from the state 5 to 6 out here, and the 6 point it will enter into the high pressure turbine. This is the high pressure turbine, and here it will expand from point 6 to 7 dash, point 6 to 7 dash. And you can see the shaft, how the shaft is happening. So the low pressure compressor, high pressure compressor, as well as the high pressure turbine. So these are having the common shaft. That means the high pressure turbine, the work output that is derived out from the HP turbine is responsible for driving the low pressure compressor and the high pressure compressor only, and it is not responsible getting a net work output. So that's the case out here. And from 7 dash, there is an external combustion, that is the reheating that we are taking, and by reheating we are again supplying some amount of heat, and the state 7 dash is the temperature at 7 dash is raised to state 8, and at state 8 it is entering into the low pressure turbine. So this is entering into the low pressure turbine and it is expanded up to the point 9 dash. So this is the point 9 dash, and the low pressure turbine, the total expansion of the gas, the total enthalpy difference due to the expansion of the gas is directly being utilized into the net work, which is coming out of the entire system. So that is the amount of work that is available for us to run our other systems. And finally, the exhaust from 9 dash is getting cooled to point 10. So point 10 here, and while having cooled to here, it is releasing that amount of heat to the air which is coming out of the HP compressor, and accordingly the regeneration process is taking place. And finally, the entire air is cooled by a particular cooler, and the system again resumes its initial starting point at point 1. So that is the entire uh, complete the process of the closed cycle gas turbine, a complete closed cycle gas turbine. And in that way we can utilize all the concepts of intercooler, heat, this regeneration cycle, reheater, everything, to simultaneously increase the specific work output, as well as increasing the thermal efficiency. So that's about the closed cycle gas turbines. Next, we will solve a few problems related to open gas turbines, and all of these problems will now actually uh, have a common strategy that we will see. If we solve the first problem, we'll get to know about the common strategy, and that will help us in solving the rest of the problems. So the first problem, which I have taken from the book Internal Combustion Engines by R.K. Rajput. So this problem states that the air enters the compressor of an open cycle at constant pressure gas turbine at a pressure of 1 bar and temperature 20 degrees Celsius. The pressure of the air after compression is 4 bar. The isentropic efficiencies of the compressor and turbine are 80% and 85% respectively. The air fuel ratio used is 90:1. If the flow rate of air is 3 kg per second, we need to find power developed and thermal efficiency of the cycle. So we have to assume Cp of air to be 1 kilojoule per kg Kelvin, and gamma of the air is 1.4, and that is same for the gas. Also the calorific value of fuel is 41800 kilojoule per kg. So let us understand this question. Let us take 1 minute, and after that I will solve this question. Okay, then let us solve this question. So the values that we are given is that the inlet pressure, the inlet temperature, the final pressure, the compressor efficiency, turbine efficiency, airflow ratio, airflow rate. So this is the TS diagram, and this is the compressor part, this is the turbine part. Now, using these values, we will first solve for the power developed, and for that, we will follow this particular strategy. First, we will have the isentropic process in here. So this is an isentropic process 1 to 2 in the compressor part. So we will solve if the process would have been isentropic, the ratio of T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma that we get from the thermodynamic relationships, and that value will be 1.486. So the temperature T2 would be 435.4 Kelvin. So this is T2, but that is not the actual temperature. We have a this efficiency, thermal efficiency of the compressor as 80%, and we'll have to utilize this value to get the value of T2 dash. So now eta compressor we know to be T2 minus T1, T2 minus T1 divided by T2 dash minus T1. So that is the value, and we know the eta compressor, so we will have to solve for T2 dash, and accordingly T2 dash is equal to 471 Kelvin. Next, the heat supplied by fuel is equal to the heat taken by the burning gases that we know. So the heat supplied by the fuel will be equal to mf into the calorific value of the fuel and the heat taken by the burning gases. Now with the burning gases we have the burning gases means the air as well as the fuel that has entered, so ma plus mf into the cp, that is the specific heat of the combined gas, now into the temperature difference. The temperature difference is from T2 dash to T3, so that the temperature difference becomes T3 minus T2 dash, and accordingly we take mf to the right side, it will divide, and we have ma by mf, and we know that ma by mf is the air fuel ratio, right? We are given the air fuel ratio as 90:1, we can directly utilize this. Then we need to solve it for T3 out here, and accordingly we get T3 to be 930 Kelvin, that is the highest temperature in this particular cycle. Then we will again utilize the concept of this isentropic process in the turbine part in order to find the values of T4 dash, and let us see how. So first we will have an isentropic process T3 to T4, so that can be related as with the pressure as T4 by T3 equals to P4 by P3 whole to the power gamma minus 1 by gamma equals to 1 by 4 to the power 0.4 divided by 1.4 equals to 0.672, and accordingly we know the value of T3 now, so T4 becomes 930 into 0.672 equals to 624.9 Kelvin. So that's great. We got the value of T4, but that is not actually the temperature because there are certain efficiencies related to the turbine as well. And we will consider this efficiency now like this. So eta turbine equals to T3 minus T4 dash, T3 minus T4 dash divided by T3 minus T4. So that is the actual work done divided by the isentropic work done. So always lesser by greater, right? This is lesser, this is greater. So that's how we will also see to this. And here we know all the values except T4 dash. We will solve for T4 dash, and finally we will get the value of T4 dash to be 670.6 Kelvin, right? So now we have this value. Next we need to calculate the since we have all the values, we will just simply have to calculate the work done of the turbine, that is mg into cp into T3 minus T4 dash. The mg is the mass of the hot gases formed per kg of air. So accordingly if 1 kg of air is utilized, then we have 90 kg of fuel, right? Sorry, 1 kg of air is now utilized, then we have 1 by 90 kg of fuel. So that's how we will have to think about it. So 90 plus 1 divided by 90. So basically 1 plus 1 by 90 and into 1, that is the Cp of the gas is same as that of air, and the temperature difference between T3 and T4 dash. And accordingly, we have the work done by the turbine to be 262.28 kg per kilojoule per kg of air. Now the work done by the compressor, it is simply dependent upon the air. So Ma into Cp into T2 dash by T1, so T2 dash minus T1, and accordingly we have 471 minus 293 this part, and we will get 178 kilojoule per kg of air. Just see the values, right? Just see the values. Out of 262, 178 is consumed in driving the compressor. So the net work is only 84 kilojoule per kg, even though the turbine is producing so a higher amount, almost around 3 times that of this net work. Still, 2 times is getting consumed in the compressor itself. So that is a very huge amount in a gas turbine. So reducing the work done by a compressor, as you can remember in my previous parts, so by intercooling method, it will actually reduce this work done, and accordingly the net work will increase. So the net specific work can increase by reducing the compressor. That's why the reducing the compressor work is that much important. Next, the power developed can be given as the work net, that is in kilojoule per kg of air. We now know the flow rate of air is 3 kg per second. Simply we multiply by 3, we will get in kilowatts. So that is 252.84 kilowatts. So that solves for the first part, the power developed. Next part is the thermal efficiency of the cycle. For that, I think we have to calculate the heat supplied. So let us see. The thermal efficiency of the cycle, obviously you can do it as a homework. So you will have to calculate the heat supplied, and the heat supplied can be calculated simply by mg Cp into the temperature difference is T3 minus T2 dash, and by that you will get the heat supplied, and simply you will divide the work net divided by heat supplied, you will get your thermal efficiency of the cycle. So that part I haven't shown here. You can go in home and you can do it as a homework, and you will find the value is lesser than 1, or even much lesser than 1, and you have a check about it. So the next part is, the next question is, a gas turbine unit has a pressure ratio of 6:1 and a maximum cycle temperature of 610 degrees Celsius. The isentropic efficiencies of the compressor and turbine are 0.8 and 0.82 respectively. We need to calculate the power output in kilowatts of an electric generator geared to the turbine when the air enters the compressor at 15 degrees Celsius and rate of 16 kg per second. We have to take the value of Cp to be 1.005 kilojoule per kg Kelvin and gamma equal to 1.4 for the compression process. And we take 1.11 kilojoule per kg Kelvin as Cp and gamma as 1.333 for the expansion process. So in the compression process, we have to consider only for the air, so that's different than as of the expansion process, where we have to consider both for air and fuel as a mixture, that is the gas. So you we take a minute to understand this question, and after that we will see how to solve this question. Okay. Let's see. I just joined. No one has joined. Okay. Okay, then let us solve this question. So this is the schematic, and these are the values which are given. So the schematic clearly shows that the air is entering at 288 Kelvin at the pressure. Is the pressure mentioned? Pressure ratio is given 6:1. Uh, if the pressure ratio is given, obviously we do not need anything more. We will see to that 288 Kelvin, it is going at 2 dash, it is getting compressed. After that, it is getting heat from the combustion chamber 2 dash to 3, and 3 to 4 dash, it is expanding, and again it is getting out as exhaust. So the highest temperature is 610 degrees Celsius. So plus 273, that is the 883 Kelvin, and you can see this is the highest temperature range. For the compression process, it is these are the values given. For the expansion process, these are the values given. Now let us understand this, that in order to evaluate the net work output, it is necessary to calculate the temperature T2 dash, T2 dash and T4 dash. To calculate the T2 dash, we must calculate first T2 and then use the isentropic efficiency, and that is the whole strategy. So in order to find, you will be given the inlet, you will be given the highest this temperature or the amount of heat added, some way to calculate that, and you will eventually have to find the value of T2 dash and 4 dash in order to find the work output and the thermal efficiency. So that is the whole strategy. So first we will consider for the compressor part, and as we have done in the previous problem, for this also we will consider the isentropic process 1 to 2, and we will find the relation between the point 2 and 1 in terms of temperature and pressure as this. There is a thermodynamic relationship we know very well, and after that we will get the value of T2 as 481 Kelvin. Next, we will consider the compressor efficiency, and this is the formula that we have already known, and we will simply put in the values, and we will solve for T2 dash now, and accordingly we will find that T2 dash is equal to 529 Kelvin. T2 dash is 529 Kelvin. You can see 481 Kelvin is T2, and due to the isentropic thermal efficiency of the compressor, it we need to give a huge amount of heat is being added up unnecessarily in order to elevate to that pressure. That's why the temperature raises to 529 Kelvin out here. Next, if you see, if you do the same way for the turbine part, so you will have a isentropic relationship between state 3 and 4, and you can use it based on temperature and pressure. Since the pressure ratio is given, we need not worry about the individual pressure values, and finally we will get the value of T4 as 564 Kelvin, and the turbine efficiency is T3 minus T4 dash divided by T3 minus T4, and accordingly if we put the values, we'll find that the value of T4 dash is equal to 621 Kelvin. 621 Kelvin. Then if you know the values of T4 dash, T2 dash, T1 and T3, we can simply calculate the work done in the compressor, work required by the compressor, then work output by the turbine, and the heat supplied as such. So work compressor is Cp into T2 dash minus T1, T2 dash minus T1, that is equal to 242.2 kilojoule per kg. Next, we have the work output by the turbine, that is Cp in T3 minus T4 dash to T3 minus T4 dash, that is equal to 290.4 kilojoule per kg. Mind that the Cp value that they use for the compressor is only corresponding to the air, so the value is 1.005, and the Cp value used for the turbine is that of the gas, that is 1.11 uh, 1.11 kilojoule per kg. Kelvin, kilojoule per kg Kelvin, sorry. So next we have the net work output as work of turbine minus the work of compressor, that is 48.2 kilojoule per kg, And next we have, we can convert that into kilowatts by multiplying with the rate of airflow, that is 16 kg per second. We simply multiply with 16 and we will get the 771.2 kilowatt is the net work output by this gas turbine. Next is the next problem, where it is stated that a gas turbine unit receives air at 1 bar and 300 Kelvin and compresses it adiabatically to 6.2 bar. The compressor efficiency is 88%. The fuel has a heating value of 44186 kilojoule per kg and the fuel air ratio is 0.017 kilojoule per kg of air. The turbine internal efficiency is 90%. Calculate the work of turbine and the compressor per kg of air compressed and thermal efficiency. For products of combustion, Cp equals to 1.147 kilojoule per kg Kelvin and gamma equals to 1.333. That is for the combustion process, and for air I guess we have to use the same value, 1.4, and gamma is 1.4 and the Cp value is 1.005. Okay, then let us take 1 minute and try to solve this problem. I will solve the problem after 1 minute. Okay, then let us solve ah, this question. So, this is the TS diagram of the problem. So we are given that uh, at initially at 1 bar and raises to 6.2 bar. So this is 6.2 bar, this is 1 bar, and the highest temperature is it given. Initial temperature is 300 Kelvin. Then is the highest temperature given, or that we have to find? Let us see. Oh, okay, the fuel has a heating value of 44186 kilojoule per kg. So we are given a means to calculate how much is the heat supplied to the state 2 dash in order to get the state 3, and in that case what will be the maximum temperature. So that the means to calculate the maximum temperature are given. So next, the same strategy, we'll have the isentropic compression process 1 2. We'll consider that. We will find the value of T2 to be 505.2 Kelvin. Next, we'll use the compressor efficiency, which is T2 minus T1 divided by T2 dash minus T1, that is this. And next is T2 dash will be equal to 533.2 Kelvin, right? Then the heat supplied will be Ma plus Mf into Cp, T3 minus T2 dash equals to Mf into C. So that is the heat supplied. And if we solve these two particular equations, we divide the left side by uh, Ma actually. So anyways, okay, we divide everything by Ma. So that way we will get this particular relationship, and we are given Mf by Ma, the fuel to air ratio to be 0.017. So we will put this value, and accordingly we will solve for T3 out here. So like I told, we have given a medium to calculate T3. So accordingly we will calculate T3 to be equal to 1268 Kelvin. So this is 1268 Kelvin. Next, uh, we will again consider the isentropic process 3 to 4 in here, 3 to 4, and we will find the value of T4. that is unknown. Since we got the T3, we will find the value of T4, that will be equal to 803.9 Kelvin. And using this turbine efficiency, that is T3 minus T4 dash, so T3 minus T4 dash, that is the actual work output from the turbine divided by the isentropic work output, that is T3 minus T4 here, and we put in the values, we are left with only the unknown 4 dash, and finally we will have T4 dash equal to 850.3 Kelvin out here. Next, the work of compressor can be calculated based on the temperature difference of T2 dash and 1. So this is Cp T2 dash minus T1, and accordingly we will have 234.4 kilojoule per kg. And the work of turbine is Cpg into T3 minus T4 dash, T3 minus T4 dash, that is equal to 479.1 kilojoule per kg. Next, the net work will be equal to work of turbine minus the work of compressor, that is 244.7 kilojoule per kg, as you can see here, right? Then heat supplied per kg of air. The per kg of air heat supplied is the yeah, we can directly calculate fuel air ratio by fuel air ratio into the calorific value of fuel. So that way also we can get, and if you also solve it in this way, that um, Ma plus Mf whole mass into the Cp into the temperature difference, in that way also if you can calculate, you will get the exact same value. So that is heat supply per kg of air. Next, we calculate the thermal efficiency, and Th, that is equal to network output, network by heat supplied, and we know the network as 244.7, the heat supplied is 751, and we will finally have a thermal efficiency of 32.57%. That is the thermal efficiency, and here this question is complete. Next, we have the other question, which states we need to find the value of air-fuel ratio in a gas turbine whose turbine and compressor efficiencies are 85% and 80% respectively. Maximum cycle temperature is given 875 degrees Celsius. The working fluid can be taken as air. So Cp is 1 kilojoule per kg Kelvin. Gamma is 1.4, which enters the compressor at 1 bar and 27 degrees Celsius. The pressure ratio is 4. Okay, the fuel used has a calorific value of 42,000 kilojoule per kg, and there is a loss of 10% of calorific value in the combustion chamber. Okay, so we need to calculate the thermal efficiency and the work ratio of the plant, assuming the Cp for the combustion process is 1.1 kilojoule per kg. So let us take 1 minute to understand this question, and finally we'll have the solution after 1 minute. Okay, then let us proceed. So this is the TS diagram again. Finally, we are given the inlet temperature as 300 Kelvin. The maximum temperature is 1148 Kelvin. The pressure ratio is 4 bar is to 1 bar, that is 4. for we utilize the same this strategy. So for the isentropic process out here, we calculate the value of T2 as 445.8 Kelvin. Then we use the compressor efficiency T2 minus T1 divided by T2 dash by T1, and we will find the value of T2 dash as 482.2 Kelvin out here. Next, we will find the heat supplied by the fuel equals the heat taken by the burning gases, and by that we can find the air fuel ratio. Let us see how. So here everything is given except the air fuel ratio part, and we have to divide whole thing by mf, and if we divide it by mf, we will get ma by mf plus 1, and all the values, other values are known. Accordingly, if we solve for ma by mf here, we will find ma by mf equals to 55.77, say 56. So the airflow ratio is 56, that is required to achieve these conditions. Next, we need to solve for the thermal efficiency and the work ratio. So for that, first we will have to consider the the turbine part as well. So we need to consider the thermal isentropic process 3 to 4 dash. Then we'll find T4 dash to be around, sorry, that is not T4 dash, it is T4. And okay, so the gross work output would be around 417 kilojoule per kg. Accordingly, we'll find the net work output to be 235, like we have already seen. Work of turbine minus the work of the compressor, and that is 235. The heat supplied will be from 2 dash to 3, that is around 739 kilojoule per kg. So simply CPG into T3 minus T2 dash. Again, from the thermal efficiency part, so the net work output divided by heat supply, that will be around 31%, and the work ratio will be net work output divided by gross work output, that is around 56.4%. So this is the fourth question. Let us move on to the next question. That is, in a constant pressure open cycle gas turbine, air enters at 1 bar and 20 degrees Celsius and leaves the compressor at 5 bar. Using the following data, temperature of gases entering the turbine equals to 680 degrees Celsius. Pressure loss in the combustion chamber is 1.1 bar. Then compressor efficiency is 85%, turbine efficiency is 80%, combustion efficiency is 85%, then gamma is 1.4, Cp is 1.024 kilojoule per kg for air and gas as well. We need to find the quantity of air circulation if the plant develops 1065 kilowatt. That's the whole work output from the plant. Okay, that's a good information, because work output is the work output from the turbine minus the work output from the compressor. We can use that into a relationship. Then we need to find the heat supplied per kg of air circulation, okay, and the thermal efficiency of the circle. We The mass of the fuel may be neglected. Okay, let us take 1 minute to sink in to this question and find the answer. Okay. Okay, then let us solve this problem. So the TS diagram is given something like this. So now using the same strategy but a little bit different is that there is a pressure loss. So initially this is at 5 bar and there is a pressure loss of zero point 0.1 bar at this point. So we will see how we can account for that. Now same for the isotropic compression part. We first find the value of T2 from the thermodynamic relationship, and then using the compressor efficiency, we finally find the value of T2 dash as this to 494 Kelvin. Next, we we find the compression this for the turbine part as well, the value of T4, but here we'll have to use the value of P3 to be 4.9 bar, not 5 bar. So we'll have to take care of for that, and we will get a value of 605 Kelvin. Next, we'll use the turbine efficiency and we'll solve for the value of T4 dash, and the T4 dash value we will get as 674.6 Kelvin. Okay, so that's how, if there is a loss of pressure in the combustion chamber, so we can utilize this particular loss in this manner. And although the loss is very less, we can see that if we can exactly consider this 2 dash to 3 as a constant pressure process, even though because the loss is quite low. Next, we can find the work done by the compressor as this. So T2 dash minus T1 Cp, that is 205.8 kilojoule per kg. Next, the work done by the turbine can be found out as Cp into T3 minus T4 dash. T3 minus T4 dash, that is 285.1 kilojoule per kg. The work net will be work turbine minus work compressor, that is around 79.3 kilojoule per kg of air. But we are given as the plant develops 1065 kilowatts, and we know now 79.3 kilojoule per kg of air is required. So we will get how much air is required. So simply we will equate these two terms and we'll find Ma to be equal to 13.43 kg. Next, the heat supplied per kg of air circulation. The actual heat supplied per kg of air circulation, that is Cp into T3 minus T2 dash, so T3 minus T2 dash divided by N eta combustion. So why this formula came up? So you see that the T3 the effect of raising this temperature 3 2 dash to 3 is due to the heat which has been received by the gas, which has been received by the gas, right? So but in order to receive from the received by the gas, it has to go through a process, a heating process, and during that heating process there will be a loss. So after the loss, whatever energy is being supplied to the gas, that is being utilized to get this net effect which we see now. So in order to get the primary supply of the energy, we'll have to divide by the eta combustion. So the actual heat supplied will be quite high, there will be some losses, and apart from the losses, whichever remains will be the net effect, will be to have the net effect of raising the temperature from 2 dash to 3. So that's why we divided by eta combustion. And let me ask you this question. Like I said before, that there is a loss in the pressure from 5 bar to 4.9 bar, that is 0.1 bar. Still they are using Cp, which is a specificated constant pressure into the temperature difference. Can we really use it, Cp? So that should be at constant pressure, right? If this would have been a 5 bar, then we would have used the value of Cp, but can it really be applied to 4.9 bar as well, with a loss of 0.1 bar? The answer is yes, because the value of Cp is not too sensitive for very small pressure difference. The value of Cp will remain almost the constant, and hence for a very small this pressure loss or pressure difference, we can still use the value of Cp like this. So we have used the value of Cp, the actual heat supplied will be 552.9 kilojoule per kg. And The third part is the thermal efficiency of cycle, that is work output by heat supplied, and that is 79.3 by 552.9, and that would be around 14.434%. So that is the thermal efficiency of the cycle. Next, we have the last question of today's session, that is, in a gas turbine, the compressor is driven by a high pressure turbine. Okay, exhaust from the high pressure turbine goes to a free low pressure turbine which runs the load. Okay, there are two turbines, means it's a reheating cycle. Okay, the airflow rate is 20 kg per second, and the minimum and the maximum temperatures are respectively 300 Kelvin and 1000 Kelvin. The compressor pressure is 4. To calculate the pressure ratio of the low pressure turbine and the temperature and exhaust gases from the unit. The compressor and the turbine are isentropic. So Cp of air and exhaust gases are 1 kilojoule per kg Kelvin, and gamma equals to 1.4. So let us take a moment to sink into this question, and I will have the solution in 1 minute. Okay, then let us solve this question. So that uh, PS diagram will something look like this. So this is the compressor parts, and we are not giving any compressor efficiency or turbine efficiency, right? So that actually eases the process. So 1 to 2 is the compression, and from 2 to 3 is the heat addition. 3 to 4 is the expansion in the high pressure turbine, which is responsible to run the compressor load. And 4 to 5 is the low pressure turbine, which actually generates the net work from the entire system. So let us now find for the pressure ratio of low pressure turbine P4 to P5. Again, the same strategy. Since the compression is driven by the high pressure turbine, we need to find the pressure, we'll have to consider the same pressure ratio. So compressor pressure is a 4, so T2 we will get as 445.8 Kelvin, and there is no compressor efficiency, so we do not have to find the T2 dash separately. Since the compression is run by the high pressure turbine, the work input to the compressor must be equal to the work output by the HP turbine. So whatever the work output by the HP turbine, that must be exactly equal to the work input by the this compressor, and accordingly uh, we can equate the work output here to the work output here, work input here, and the work output here is T3 minus T4. So we will find that the highest maximum temperature is given as 1000 Kelvin. So T3 we already know, we do not know T4. So we can find directly for T4 like this. So we have just equated, this is the compressor load and this is the work done by the turbine, and we have just equated, we are given the same um, mass flow rates of air and gas, we do not have to consider for the gas, and accordingly we will solve for T4 and we will get T4 as 854.2 Kelvin. This is 854.2 Kelvin. Okay, so for the process 3 to 4, now we know the temperature T4, we know the temperature T3, we need to find the pressure ratio of low pressure turbine and the pressure ratio of that. So P3 is equal to P2, out here, right? And uh, we will have to substitute somehow. We will see how to find that. So P3 by P4, that will be equal to T3 by T4 to the power gamma by gamma minus 1, and we will have a value accordingly 1.736. Now we will place a value P5 out here. How? So P3 by P4 is equal to P3 by P5, okay, P3 by P5 into P5 by P4, right? So that is P3 by P5 here is equal to this load, that is 4. We already know that P3 by P5, that is equal to P2 by P1, that is 4, into P5 by P4, that we do not know, P5 by P4. Now P5 by P4 equals to 1 by 4 into P3 by P4 equals to 1 by 4 into 1.736 into 0.434. So P5 by P4 we got to know 0.434, and the reverse will give the pressure ratio of the low pressure turbine, that is equal to 2.3. So the pressure ratio of the low pressure turbine, that is the answer to the first question, is 2.3. Next, the temperature of the exhaust from the unit T5. Temperature of the exhaust from the unit T5. So if we know the pressure ratio, we will see we know the temperature T4. We just have to find the temperature T5, and this is an isentropic process. So simply we use the thermodynamic relationship of an isentropic process, and from that we can find the value of T5 to be 673 Kelvin. So this was the last uh, question and the solution to the last question. So in this session, let us sum it up. In this session, we have learned the various concepts of gas turbine, that is an open cycle gas turbine, a closed cycle gas turbine. In an open cycle gas turbine, how we can increase the specific work output and the thermal efficiency, and what is the closed cycle gas turbine, how does a complete closed cycle gas turbine looks like, if we can utilize the um, all the concepts of an open cycle gas turbine, that is like regenerating, intercooling, then reheating, in order to increase the specific work output as well as the thermal efficiency simultaneously. So that concepts we have learned in this session. The next thing we have done is that we have solved a few problems on open cycle gas turbine, and we have now I hope that we have gained a few confidence in solving the open cycle gas turbine. In the next session, we will start by solving the closed cycle gas turbine, or more this extensive problems like intercooling, reheating, regeneration. We will solve a little bit tougher problems than in this session. Then we will have a complete understanding of how to solve a gas turbine problem. Uh, so that was all for today's session. So thank you, and let us meet again in the next session in the next week. Okay then. Bye bye.